UV visible spectroscopy. This machine I have at the top floor, maybe you have seen. So, what is the purpose? First of all, I will tell you what is the purpose of spectroscopic techniques. Spectroscopy is used for analysis. Sometimes we comment, this is the structure, that is the structure. We are writing into pen and paper. But how do you know that? It is written in the books. How book will know? How the book writer will know that? Isn't it? Analysis required. That analysis is done nowadays by spectroscopy. Nowadays, the latest modern technology that is used, it is called spectroscopy. One is ultraviolet. And what is spectroscopy? First of all, let me clarify. Take some matter, you want to analyze. Pass some light through that. And the light can pass through, it can reflect back, a part will be absorbed and part will be scattered. What are the options that I am telling? If you take some matter and put some certain light onto that, what will happen to the light? Either it will be reflected back, it will be scattered, it will be absorbed, it will be emitted. These are the options, right? Then how much is what happening, that you are analyzing. How much of what is happening, that you are analyzing, it is called spectroscopy. Very simple idea. Take some matter, pass light through it, do the analysis of the light. Then you can get the idea about the matter. That is called spectroscopy. Now, if you pass ultraviolet light, you get UV spectra. If you pass IR light, you get IR spectra. Okay. So, different type of radiation you are passing through the matter, and interaction between the radiation and matter is called spectroscopy. The study about the interaction of matter and radiation is called spectroscopy. Is the thing simple to you now? Spectroscopy means interaction between the matter and radiation and their analysis. That is spectroscopy. Now, ultraviolet spectroscopy will start. What is the machine? Inside, what are the different components? Let's have some idea. First of all, we start from here. This is the tungsten lamp. Lamp is the light source. You have to send light to the matter. So, this is the light source. Now, this light source can be ultraviolet light or visible light. For ultraviolet light, one type of lamp required. For visible light, another type of lamp. So, that's why at least two lamps required. One is for UV and this for visible. Normally, visible is tungsten filament lamp we are using for visible, and for ultraviolet we are using deuterium lamp. Deuterium lamp. So, here it is tungsten, here it is deuterium lamp. Both are there actually, see. Both are there together. But both will not be effective at the same time. One will be off, another will be on. Because one by one frequency will have to send. Light frequency, one by one will have to send. Which one is absorbed, which one is not absorbed, that you need to analyze to get the picture of the material. So, then you have, after these two lamps, this is either this is on, this is off, or this is on, this is off. One by one we will have to make it on and off, and machine will automatically decide. If you just give the range, within what range you are sending the light, if you can from the beginning, if you can give the instruction, accordingly the light will be made on or off, or manually also you can make it on or off. There is a lens over here that will convert the light into a single beam. Okay, lens is required to convert the light, scattered light, into a single beam. Then after that, you have a shutter. Shutter will open for a fraction of second, so that the light beam can enter and immediately it will be closed. Then only analysis can be done. If you continuously go on sending light, you will get lot of signals and scattered signals. You cannot analyze anything. That's why shutter is just like a camera front. On the camera there is a shutter, so automatically it closes and makes it on. So in the mobile camera also it is just making for a fraction of second it is making it on. The flash is only for a second. Okay. So that is happening by the shutter. Then you have the sample. Sample is kept inside the container called cuvette. C-U-V-E-T-T-E, cuvette. So this is my cuvette. Then again you have the lens. Because passing through cuvette, light again can be a little bit of scattered. Some Tyndall effect happens. Tyndall effect. That may happen. So light will be scattered once again. So that must be converged once more through the lens and then passing through the slit, a small hole, and falling onto some grating so that the grating can do the particular monochromatic light analysis and then going to the diode arrays. So finally it is going to the decoder, recorder sort of thing. Printer, plotter. That is the end, last of all. So this is the beginning, this is the end. This is the analysis of the machine, more or less. So it is see the ranges. Ultraviolet range 200 to 750, that is called UVVs. Okay. Normally, I am telling you my machine range. It is 190 to 1100 nanometer. Range is quite larger. Here it is written only 200 to 750, but nowadays modern machine is much better. Now my machine range is 190 to 1100 nanometer, much wider range. The more range, the better analysis. If shorter range, you can have only very restricted analysis, isn't it? So it is better. So this is the ranges. Normally ultraviolet visible range is 200 to 750, but beyond that also my machine can analyze. IR radiation, IR infrared, it is 2.5 to 16 micrometer. IR is in micrometer. Then you have NMR. NMR is what? MRI is a application of NMR. But what is NMR? First you have to understand NMR, then only MRI. And for understanding NMR, you have to try to concentrate your attention. I am trying to clarify. First of all, the electrons into any matter, electrons into any atom, they are spinning. That you know, half spin, plus or minus half spin, that much you know. Now, all the electrons, are they spinning always in the same direction? Some are in the clockwise, some are in the anti-clockwise direction. Achha. Are they equal energetic? Clockwise and anti-clockwise. Energetically, these are supposed to be equal, right? But no. Clockwise is slightly more stable compared to anti-clockwise. Not exactly same. Normally, literally, we say that this is this plus and minus of scheme, etc., etc. But practically is no. If you go in the finer aspect, analyze, it is found that it is the popularity of plus half is more compared to minus half. I can prove. Suppose you have 3 boxes and 3 arrows. You are filling electron. How do you write it? Up arrow, up arrow, up arrow. Have you ever written down arrow, down arrow, down arrow? Why not? No, there is no reason particularly. No reason. But found that it is practically found that plus of spin is more stable compared to minus of spin. Very slight difference, but still there. Little bit of difference is there. That difference make everything important here. Okay, that difference we are making. Now, this plus of spin is called alpha state, and minus of spin is called beta state. So electron can have alpha state and beta state. So how many number of electrons there in the alpha state and how many number of electrons in the beta state, that is called their population. Okay, population. So plus of population is more compared to minus of population. So alpha state is more populated compared to beta state. Is this thing clear now? Alpha state is more populated compared to beta state. Now that is original, we have not done anything. Now we are applying certain magnetic field. Magnetic field will have interaction with the spin of the electron motion, because electronic spin also has some magnetic field, and whenever external some magnetic field is applied, the population of this alpha and beta state gets changed. They are all getting energized because of this magnetic field. There is sort of interaction. Interaction is happening. Okay. So now magnetic field is applied above and below the material. The magnetic field is applied, and the electrons are all getting energized. And what is happening after that? We are using some radio frequency, and difference of energy between this plus of state and minus of state, the alpha state and beta state, is very little. The difference is very little. That's why normally we ignore it. Until unless it is required, we normally ignore it, right? So little bit of energy difference. Whenever you are applying the radio frequency, the population gets changed. Some of the electron from alpha state is going to the beta state, which is higher. Just like a natural tendency, it is there, it is going to the higher energy level and coming back. Here also like that. You are applying radio frequency. Due to the radio frequency, it is absorbing the radio frequency, and some of the electrons from the alpha state is going to the beta state. Then after that, you remove the pulse. Radio frequency pulse you remove. Then they are coming back. That is called relaxation. And when they comes back from the beta state to alpha state, once again, the nature is different. Material to material, the nature is different. How the beta state to alpha state are coming back, the nature is different. Accordingly, we are getting peak. And from this peak, we analyze the material. That is NMR. I think it is very complicated for you for the time being. So first, let us complete this UV. NMR is the topmost one. So first, let's complete the UV. UV phase. Most important consequence of such interaction of energy and matter. Of interaction means interaction of energy and matter is absorbed or emitted by the matter in discrete amount called as quanta. Some quantum of energy is absorbed by the material and some is emitted. That we are analyzing. UV radiation starts at the end of the visible light and ends at 2000 angstrom, 4000 angstrom to 2000 angstrom. Divided into two regions. Near UV, which is 2000 to 4000, far UV, below 2000 angstrom. Wavelength, angstrom is wavelength. UV spectroscopy involved with electronic excitation. What does it mean? The last sentence, UV spectroscopy involved with electronic excitation. That means you have a sigma level, sigma star level, pi star, and n level. The electronic transition happening from sigma to sigma star, pi to pi star, pi to sigma star. This type of phenomena restricted into ultraviolet spectroscopy. Acha, at this moment, I can clarify one thing. Why water is colorless? Why water is colorless? All of you know water is colorless. But why water is colorless? Because there is only possible transition is sigma to sigma star. No other transition possible because there is no double bond. Water molecule, there is no double bond. There is only lone pair and there is only sigma and sigma star level. So what are the possible transition? N sigma star and sigma sigma star. There is no other possibility. N sigma star is also possible. N sigma star and sigma sigma star. This transition happening in the ultraviolet region, and ultraviolet is not visible. That's why it is colorless. You cannot see ultraviolet change, absorption, etc. Our eye, naked eye, cannot see the ultraviolet absorption. That's why you can see water is colorless. Whatever transition happening falling in the UV. If it falls into visible, we get it colorful. Like chlorophyll is colorful, green. That is because the chlorophyll electronic transition happening in the visible region. That's why you can see it is colorful. Our blood is red because of the same reason. The colorful, that electronic transition that is happening is always in the visible region. Let it be for chlorophyll, let it be for our blood, whatever colorful things we know. Everywhere the same thing is happening. That's why you can see it is colorful. And whenever it is falling in the ultraviolet region, it is colorless. That's why our chromium, manganese, nickel, all these compounds are found to be colorful, whereas sodium, potassium, calcium, magnesium compounds are all found to be colorless. Because their transition is not happening. Why not transition happening? Because D energy levels are not available there. D levels should be there. So whenever you have partially filled d orbital, their d transition is possible, which is not possible for sodium potassium, because d orbitals is not available for such transition. It should be available for transition. Theoretically it may be there, but it is not available for any transition, and that's why you cannot see that color. So color thing is that. What is the color? Color means what? Some sort of sensation coming to us. That is color. We can sense it, right? That sense we can do if it is into our range. You can hear, listen to me, because I am talking and that is into your audible range. If it is out of range, you cannot listen. So everything is like that. Light also is in the range. That's why you can see. If it is not out of the range, you cannot see. Absorption and emission spectra. Absorption spectrum means you have some matter. Allow the light to pass through it. Allow the light to pass through it, and after that, it is going into some photographic plate and getting some spectroscopy. That is called absorption spectroscopy. Light is passing through the matter and falling into photographic plate. Directly you are getting some spectrum. That is called absorption spectroscopy. Spectroscopy is the scopy. When you are using the term spectroscopy, means a total type of discussion. Spectrogram, that is the photograph. Spectrophotometer, the machine. All are very close but not same. Spectrum or spectrogram, that is the picture, the plot, the graph that is found, the final output. Okay, that is spectrum. Spectroscopy is the theory, our discussion, that is spectroscopy. And spectrophotometer is the machine where we are doing the analysis. That is the machine. Now, what is emission spectra? Spectra is the plural form. Spectra, spectrum, spectra. So, spectra is the plural, spectrum singular. Now, emission spectra. What is that? You are having some matter which is already excited, heated up or something like that. So, in front of that you put some photographic plate and remove the source of any sort of radiation. Then what will happen? From the excited matter, may be heated up, or so energy radiation comes out and automatically falling onto the photographic plate, and you are getting some spectrum. That is called emission spectra. So, it is emitted from the matter. It is coming out from the matter. That's why it is called emission spectra. Absorption, matter is absorbing. Rest you are getting. That is absorption spectra. Emission spectra, from the matter itself, the radiation is coming out. That is giving you some spectrum. That is emission spectra. So, these two spectrum we are using into atomic spectra analysis. Atomic spectra, Lyman-Balmer Paschen bracket full series. There also we have got the spectrum. There also we can use either absorption spectra or emission spectra. These are some certain terminologies: wavelength, frequency, wave number. I think these things are known to you, so I can skip. Then this is the range. Different color, you see. If I say orange, orange means 595 to 610. If I say green, so then 500 to 560. These are the what? Nanometer wavelength. So that means 500 is also green, 560 is also green. So that means our eye cannot recognize the difference between 500 and 560. We can understand that it's green. Okay, you can see the green, but it contains so many in different wavelengths. So that can be photochromatic. What is the meaning of photochromatic? Photochromatic means, Chano, if it light falling onto some matter, it is becoming colorful. When light falling onto some matter, it is called colorful. That is called photochromatic. Monochrome, terms go jante hobe. Monochrome, single color, right? Single color. But that single color also contains so many wavelengths. So this monochromatic lamp, if you use, then also you need to separate each and every individual frequencies by some sort of mechanism that is called grating. Grating, grating. By grating, one by one frequency you can send into the matter. That is necessary. If you just send some patch of light, you cannot get anything. Because exactly which one is absorbing, that if you don't understand, then you cannot give any conclusion. That's why one by one frequency you have to send into the matter. Then you have to analyze which one is actually absorbed and which one is not absorbed. The one that is maximum absorbed is called lambda max. Lambda m. Okay, lambda m. What is lambda m? That particular frequency is absorbed by the material. So from that you can conclude, well, so this one is absorbing into this particular one. That means it has got that OH group, or it has got this type of double bond. There is a alternative double bond. No, there is no alternative double bond. There is a the double bond there, two double bond or more double bonds there, but this is not alternately placed, not adjacent. So that type of conclusion you can draw by this analysis. This particular the machine, this UV spectroscopy is very much effective to analyze that impurity in a drug sample. Impurity in a drug sample. So if you have some drug and how much is the impurity into that bulk drug, if you want to analyze, the ultraviolet spectroscopy is the best one. There are so many other spectroscopies also. This is the what is the utility of ultraviolet that I am telling, and what does it analyze particularly ultraviolet spectroscopy? Double bonds, position of double bond, number of double bonds, adjacent double bond, alternative double bond, conjugated double bond, non-conjugated double bond, type of phenomena. Got the idea? Position of double bond or triple bond, unsaturation present or not. That much of idea you can get from this particular spectroscopy called ultraviolet spectroscopy. And what does it do? Electronic transition. Electronic transition. Sigma to sigma star, pi to pi star, pi to sigma star, this type of transitions. Electronic transitions. Now, a particular molecule, how many types of movement it has, or how many types of energy it has? One is electronic energy, that is the level itself, electronic level. Then vibrational energy associated with it, and rotational energy associated with it. Now, you know our microwave oven, we reheat the food. Do you know how it is reheating the food? It is sending some microwave energy. That microwave energy is absorbed by the water molecule, and water molecules are already having some rotational motion. They are enhancing the rotation of the molecule. That way molecules are colliding with each other because of very fast rotation. They are colliding with each other. That way the heat is getting dissipated throughout the food, and the food is heated up from inside, not from outside. Normally we are using flame to heat the food, so it is from outside. So that's why maybe the outside is charred, but the inside is still cold. It happens, na? If you use into some pot, you take the cold food from refrigerator, pour it there, and just stir it. You will find that after some time the outside is getting charred or burned, but still inside is cold. But that is not happening in this case for microwave. For microwave, the heating is done from inside. So inner portion is more heated up compared to outside. So here this is some metal or molecule. Metal, not metal, molecule. Some molecule absorbing some light energy, h nu, some quanta, getting energized. This energized molecule giving some new species. By relaxation, after that M star is converted to some new species. Sigma electrons, they are in the sigma bond, pi electron, they are in the pi bond, and n electron is lone pair. Possible transitions, sigma sigma star, n sigma star, these are allowed. Usually they are all allowed, but pi and pi star is forbidden transition. Though energy requirement for pi to pi star is very small, is supposed to be very easy, but because of symmetry reason, this transition is forbidden. Symmetry, orbital symmetry. Okay, so these are the transitions possible: sigma, pi, n, pi star, and sigma star. This is the different levels. From this level, you understand which one is more energetic and which one is less energetic. So now, what are the possible transitions? Sigma to sigma star. Sigma to pi never happen. Why? Because pi is in one plane and sigma is in another plane, perpendicular. So this transition is not happening. Transition means jumping electron from this level to that level. That is transition. So sigma to pi not possible. These are the possible transitions, and out of that, this one is forbidden. So that means it will happen very small. Forbidden means it will happen very small, and usually that is happening. It is allowed transition. So the actual happening is very large. The occurrence is large. Epsilon max 10 to the power 4 or more. Allowed transition have an epsilon max. That means the how much is happening that I was telling. that is the represented by the same value epsilon, that is 10 to the power 4 or more. Pi to pi star in 1,3-butadiene exhibit absorption, allowed transition, forbidden transition less than 10 to the power 4, epsilon value, absorption value. So energy required for these different transitions, sigma to sigma star is the highest, the gap is very large, n to sigma star, then pi pi star, and then n pi star. N pi star transition can happen, this is allowed, and then probably this happens the most. Then you have, this is the instrumentation, source, monochromator, sample compartment, detector, recorder. I am not going into detail because at the beginning I told you. Now this is the sample, they are in the sample as well as solvent that we keep here. This is the light source, wavelength selector, then passing through the material, the solvent, the sample, then photo detector, and then readout. Readout means the spectrum form there. This is the light source, prism, then monochromator, then one by one, ultimately it is going to recorder. This is actually, okay, I will continue in the next class. So just showing, this is the starting, so I not start it today. So this is the light passing into two different, one is sample and another is the reference. It is called double beam spectrophotometer. Double beam, reference is required because what solvent you are taking, depending on that you will get the absorption. Solvent, so effect of solvent you have to deduct. Effect of solvent you need to deduct. So same amount intensity of light should pass through at the same time through the reference as well as sample. So from the difference we can get the better signal.